Hello, my name is Eric Georgin. I am involved in the JRP BioFmet dedicated to new metrological methods for biofuel materials analysis. Today, I will be delivering a presentation on the fundamentals of humidity and moisture measurement with a focus on the reference techniques implemented at LNE-CETIAT. In metrology, direct measurement techniques refer to methods that enable the measurement of the measurand of interest without any intermediate quantities. This means that the physical quantity being measured is obtained directly from a calibrated instrument without the need of any additional steps. Direct measurement techniques are considered the most accurate and precise way of determining the value of a physical quantity and are often used to directly realize or define the primary unit of measurement for that quantity. It implies the use of reference or primary or absolute measurement techniques. Primary techniques are typically used to calibrate secondary or indirect moisture or water content measurement techniques. Thus, traceability to the international system of units can be established. Now, few words about traceability. Traceability is commonly visualized as a pyramid with the reference of the SI unit at the top and the end users will rely on daily measurements at the bottom. Between these two extremes lie various intermediate steps or levels which play a crucial role in connecting the highest level to the end users. Traceability is the property of a measurement result that enables it to be linked to a reference through an unbroken chain of calibrations. In contrast, the process of transmitting this traceability from the reference to the end users is known as dissemination. Definitions of traceability are proposed in the International Vocabulary of Metrology, also known as VIM. Now, as we have presented what is a direct or a primary or a reference measurement techniques, and as we have defined the traceability, let's see how we can practically ensure this traceability with reference techniques. The first one is the loss and drying. The loss and drying technique is a gravimetric method which involves measuring the mass loss of a sample as it is heated to drive off moisture. The typical steps involved are the following. First, sample preparation. A representative sample of the material is selected and weighed on a balance to determine the initial mass. The sample is then placed in a suitable container which was initially cleaned, dried, and weighed. Then you have the drying. The sample is then placed in an oven and heated to a specified temperature for a specified amount of time. The temperature and time of heating depend on the type of material being tested and the specific standard or method being used. Then you have the cooling. After heating, the sample is allowed to cool to room temperature in a desiccator to prevent moisture uptake from the atmosphere. Then you have the weighing. Once cooled, the sample is removed from the oven and weighed again to determine the final mass. The mass loss due to moisture evaporation is calculated by subtracting the final mass from the initial mass. Here you can see the evolution of the loss on drying as a function of time. So here we can reach a kind of plateau which corresponds to the end of the drying process. And remember, this method is widely described in different standards and is very sensitive to the drying temperature and the time. In this technique, the measurement being measured is moisture content, which refers to the total amount of water in a material, including any volatile organic compounds, also known as VOCs. This measurement technique will represent the total amount of moisture in the material. Depending on the context, moisture content can be expressed on a dry basis, that is to say, as a percentage of the material's dry weight, or on a wet basis, that is to say, as a percentage of the material's wet weight. Both quantities, whether expressed on a dry basis or wet basis, can be related to each other using the equation presented in this slide. The following table presents the typical uncertainty associated with loss on drying for the analysis of wood pellets. In this example, the moisture content is approximately 6.04 gram per 100 gram, and the expanded absolute uncertainty is approximately 0.26 gram per 100 gram, which is equivalent to a relative expanded uncertainty of approximately 4.3%. Now, let's discuss about chemical analysis techniques. Chemical analysis techniques are another family of methods available for determining moisture content. Coulometric Karl-Fischer titration is a well-known and widespread method for measuring water content in a wide range of samples, including solids, liquid, and gases. This method uses Karl-Fischer reagent which react with water specifically in the sample to produce an electric current in the electrochemical cell. The amount of current is directly proportional to the amount of water present in the sample. Coulometric Karl-Fischer titration is typically used for measuring very low level of moisture, usually below 1%. Faraday's law is directly related to coulometric Karl-Fischer titration method, as it describes the relationship between the amount of electric charge passed through an electrochemical cell and the amount of material being deposited or dissolved at the electrodes. In coulometric Karl-Fischer titration, Faraday's law is used to determine the amount of water in the sample based on the amount of electric charge passed through the cell during the titration. Here, the coulometric Karl-Fischer titration is combined with an oven and also a carrier gas to evaporate and collect the moisture from the sample to the electrochemical cell. This technique is often combined with chemical analysis. The following table presents the typical uncertainty associated with oven coulometric Karl-Fischer titration of wood pellets. In this example, the moisture content is approximately 7.16 gram per 100 gram, and the expanded absolute uncertainty is approximately 0.15 gram per 100 gram, which is equivalent to a relative expanded uncertainty of approximately 2.1%. Another chemical analysis is the electrolysis of H3PO4. This is a chemical analysis technique that can be used to measure the water content in a sample based on selective electrolysis of water molecules. This method involves heating the sample in an oven to evaporate the moisture and then reacting the water molecules with P2O5 coating to form H3PO4. In the electrolytic cell, H3PO4 molecules are dissociated into hydrogen and oxygen. The amount of electric charge consumed by the electrolysis is measured as a function of time and integrated to yield the total charge, which is directly proportional to the amount of water in the sample according to the Faraday's law. Thus, water molecules are selectively electrolyzed, and the amount of current passing through the cell is proportional to the amount of water in the sample. This technique can differentiate between different bonding forms of water, such as free water, physically bound water, or chemically bound water. Electrolysis of H3PO4 is typically used for measuring low level of moisture, usually below approximately 10%. Faraday's law is directly related to this method, as it describes the relationship between the amount of electric charge passed through an electrochemical cell and the amount of material being dissolved at the electrodes. In this method, Faraday's law is used to determine the amount of water in the sample based on the amount of electric charge passed through the cell during the electrolysis. Here, this slide presents an example of the analysis performed with the H3PO4 electrolysis technique for kaolinite clay. In this graph, the lower part shows the temperature profile as a function of time, and the upper part shows the electrolysis current as a function of time, which is directly proportional to the water content in the material. As can be seen, 4 peaks are measured following the temperature profile, allowing for the identification of 4 types of water bonding forms: free water, the first bond water, the second bond water, and the third bond water, leading to this quantification of each bonding forms. The following table presents the typical uncertainty associated with the H3PO4 electrolysis for wood pellets. In this example, the moisture content is approximately 7.12 gram per 100 gram, and the expanded absolute uncertainty is approximately 0.14 gram per 100 gram, which is equivalent to a relative expanded uncertainty and approximately 2%. We have seen in this presentation an overview of 3 different reference techniques that can be used in a calibration laboratory for ensuring the traceability to a site. We have defined as well what is the traceability. I hope you enjoyed, and thank you very much for your attention.